So I run a company called Pepperdata, which collects data from big data servers. So think about all the things that run MapReduce and Spark and things of that sort at scale. So think about people who have thousands of nodes running these very complex distributed jobs, and they'd like to figure out what goes wrong with these jobs and how to predict what might go wrong with these jobs. So as a result, we collect tons and tons of data from these guys. How the hell do you use this stuff? I'm getting old and I can't see. Next. There we go. So I'm going to talk a little bit about the kind of data that we collect and what we can actually do with the data in order to make it easier for us to make running these jobs much, much more efficient on these clusters. The talk is basically background, so you understand exactly the type of data that we're dealing with. And then I'll separate it into two things, univariate time series and multivariate time series. And the reason for doing that is it turns out that the approaches for both are actually dramatically different. And then we'll talk about how we actually put the stuff together. So background. We collect data from every single JVM and every single task that runs on these machines. The kind of data that we collect are things like all the virtual memory, every single fault that actually occurs on the machine, the number of bytes that are read, the number of bytes that are written, all the network traffic, how much traffic there is on a given NIC, how much traffic there is on a given I/O port, every single thing that happens on that machine. And we report that back to our AWS backend, which ingests all this data and then makes it accessible and queryable to everybody that uses it. Give you an idea of the size of the data set. This is from one of our customers, 570 nodes, about 20 tasks per node, 300 metrics. We sample it roughly every 5 seconds. It gives us 41 million data points per minute. And this is a small cluster, right? If you aggregate it over the number of clusters that we've got that we're looking at, and by the way, this number goes up because we keep selling more, we have about 25,000 clusters that we watch like this. We collect about data on about 50 million jobs per year, and so far, 300 trillion data points. That's a lot of data. That's a lot of first-party data that we have. And as I said, it's very, very granular data about every single thing that's happening on this cluster. The time series sort of looks like this. It's kind of boring, especially compared to the last talk. I have no funny slides. The first one is, the number of active tasks. The second one is like HDFS reads. Then it's the network traffic. The next one is the CPU, and the next one is virtual memory. These are the kinds of data sets that we collect. And as I said, there's about 300 of them coming in from every single node every 5 seconds for every task. So the characteristics of our data set are interesting. It's highly variable in length, right? So we can have data sets that are only 10 data points long. Something might happen to the network. We might not get reporting data back, so there's missing data. Or we could be, there could be a job that could be running for 24 hours and is reporting back to us every 5 seconds for every single thing that's coming on a 4,000 node cluster. So it could be tens to hundreds of thousands of data points that actually come in. Highly, highly variable. We have missing data. Because what happens sometimes is an interrupt happens, a machine goes down, a disk has an issue, and therefore something stops reporting for a little bit of time. And so there are gaps in the data that we wind up getting. And of course, there's noise in the data because the way you poll the data results in sometimes the counters in the machine are not necessarily as accurate as you need them to be, or your counters aren't, and as a result, you get lots of noisy data that comes across. So the problem that we want to solve is, how do I take all of this data that comes across all these different jobs and classify these jobs into clusters so that a scheduler can say the following: all of these jobs have the same characteristic, and therefore you probably don't want to put them to run at exactly the same time. And by the way, when I say a scheduler, often the scheduler is a human being, right? So big data clusters, they run, there are all these queues that they actually manage. Jobs get actually put onto these queues, and what you don't want to have happen is all the queues have exactly the same type of job, because now everybody's going to hit memory at the same time, everybody's going to hit CPU at the same time, and performance is going to go to pot. So you don't want that to happen. More importantly, we want this to be automatic. We want to be able to characterize these jobs, understand them, so that the actual scheduler that originally put the jobs into the queues, not the human scheduler, can actually take appropriate action to make sure that the same saturation doesn't take place. That's the fundamental problem that we want to solve. And it's a large problem, and it turns out to be a fairly interesting and hard problem. So let me start by talking about univariate time series. First of all, I should let you know, I don't spend all my time doing machine learning. I did this, by the way, with 2 students over the summer, one of whom happens to be my son, which was kind of fun. A grad student from UCI and and my son, we actually put all this stuff together. I've been doing machine learning for a few years, so I have some background, but I don't do it on a full-time basis, so that's the proviso. Univariate time series. So it turns out we started looking at what do people do for univariate time series. And you look at recent publications, and what you find is there are 2 basic approaches that people have used it. One is to transform the time series into an image, and I'll talk about that in more detail because I leverage that. The second one is to transform the time series into a bag of patterns. And almost everybody deals with one data set, which is called the UCR data set. It consists of about 82 time series, and it's about 10,000 series altogether in there. Or the largest one is about 10,000. I think it's 8,500 to be precise, and is less than 2,000 data points per series. So it's actually fairly toy compared to the stuff that we're dealing with. Now you have to step back and ask, for our case, what I wanted to do was build something where I wasn't pushing the science. What I wanted to do was build something where I could actually get something out the door and make it useful very quickly. The time constraint was we wanted to do this all in 3 months, start to finish. Right? And so the results I'm presenting you are actually everything that was done start to finish within the time bound of 3 months. So let's talk about time series and images. So, if you take a look at a time series, the obvious thing to do is, hey, it's a plot. Let's use that. That's an image. Certainly tried that. Guess what? The results suck. The next thing to do is to say, hey, it's a time series. Let's break it up into chunks. And let's take a spectrogram of each of the chunks and see what we can do. Well, it turns out the results suck. So there are these clever people who came up with these interesting representations called, and there are the 3 of them are Gramian angular summation fields, difference fields, and also Markov transition fields. And I'll talk about those in a little bit of detail in a bit. And then what they do is they take this image, they then train a CNN, and a very specialized CNN, which takes a long time to train, and they get a set of results out on the other side. So I thought, man, this is pretty interesting. Let's continue exploring this thing. So what is a Gramian angular field? So first thing you do is take the time series and you normalize it, right? So you chunk it down into a pattern that you understand. Then take that, and the clever thing that you do is you put it into polar coordinates. Once you put it into polar coordinates, what happens is sort of time goes this way, and you wrap the time series around itself in polar coordinates. Then what they do is they look at the difference between 2 different points, and they look at the sine of the difference or the cosine of the difference, depending on whether you want this part of the triangle or the other part of the triangle. And then that becomes, if you do that for every pair of points, what that does is it gives you a matrix. Now you interpret that matrix as an image, right? It's kind of clever. And then what they do is they pump the combination of these images, the difference field, the summation field, and then the other thing that you do is the thing that gets done in machine learning all the time is you take a look at your time series, you quantize the y-axis. Once you quantize the y-axis, then what you do is you say, well, how often does state A go to state B across my entire time series? That's your Markov transition field. You interpret that, you normalize that, you interpret that also as an image, and now you have 3 sets of images. They put those 3 sets of images together, and then they run a CNN through this thing. It's kind of clever. So that time series in a Gramian angular difference field turns into that. And by the way, it's highly symmetric. And the reason is because it's either the cosine of the sum of the angles or sine of the difference of the angles. So obviously, you're going to get symmetry around the thing. So that's one approach. The second approach is also pretty clever. What they do is they divide the time series into a set of windows. And there's lots of clever things about how I divide things into windows and whether the windows are static or dynamic. But they take a window, they generate the Fourier transform, kind of nice, because now you're in frequency space. They get rid of the sort of the low pass, they run a low pass filter through this thing. Now they take the Fourier coefficients, they quantize those. When they quantize those, and by the way, there's lots of interesting cleverness, and it's worth reading the paper because it's really cute. They quantize the Fourier coefficients, and then what they do is they map each of these sort of quantized areas as letters. So you can think about, you've got your Fourier coefficients laid out this way. One has a value here, here, and here. You quantize the y-axis, and you say the first one is A, the second one's B, second one's C, and so on. And now each window gets turned into a word. And words, then the entire time series is now a sentence. And now you've got a really nice embedding that they've created to be able to go do that. And guess what? Next thing it's obvious to be able to do, they apply logistic regression to this thing, and they wind up doing classification. Very clever. Much too clever for me, especially in a three-month time window. So what I decided to do was something a little bit different. And I said, well, there's lots of interesting stuff that's available on the web that one can use. Google has a CNN they've already trained. I wonder if we could use that. And we could get some interesting results out of that. Let's see what we can mix and match to produce an interesting set of results. So we experimented with the difference fields, all of the different image representations, came up with the fact that the difference field was actually the one that captured the most features, put it in through Google CNN, pre-trained CNN. So this is a CNN that's been trained on, Inception, right? So it's dogs, cats, all kinds of interesting stuff. Take the final layer off, and you get an embedding into a 2048 dimensional vector space. So that's the first thing that happens, sort of pre-process image into this 2048 dimension vector space, and then do something really trivial, put that into a multi-layer perceptron that has 2 hidden layers in it, and see how well we can do. And the only thing we're training now is just that MLP. Turns out, it's actually pretty good. So these are accuracies for a subset of that UCR data set. So that UCR data set, by the way, has stuff for handwriting recognition and sort of image stuff, and then there's a bunch of stuff that what I would call real-time series collected from sensors. That's basically the kind of stuff that I'm displaying here. And what you see here, which is fascinating, is that the best approach, which was the approach that did the bag of words trick, has a 91.1% accuracy. Our simple approach of just taking stuff that's off the shelf with a very simple MLP at the end of it produces 89.8% accuracy. Right? Kind of interesting. And that fancy approach of taking the difference field, the summation field, and also the Markov field, putting it all together, running it through a custom CNN, has an 86.4% accuracy. It was a kind of interesting set of results. If you look overall and you look at every single thing that I found that was published on the UCR dataset, it turns out that we produce amongst the top 4 or 5 accuracies across the entire dataset. Again, simple approach, off the shelf. The other thing that's interesting is to compare the amount of time that it takes to train. And by the way, I'm horrible at making slides, so cutting and pasting is not my thing, so that's why these things look terrible. What's interesting is if you look at that little blob that says PD, what that tells you is that for the amount of accuracy that we generate, we also have some of the fastest training time. And oh, by the way, in the training time, I'm including converting the time series into the image, running it through the CNN, and then running it through the MLP. So it's a full boat solution here, right? And it's pretty good because compared to the solutions out there, we're really on par in terms of training time as well. Simple approach, and it works, right? So we tested it and said, well, we feel good about this. Let's see what else we can do because our training set, our data set is actually multivariate. So let's see what happens in multivariate. Let's talk about that next. As I said, the interesting thing is that the literature is broken into 2 different components. One has univariate, the other one is multivariate. Let me talk about the multivariate side. So the two most recent cited approaches are the first one using this thing called an echo state network. I'll talk about that in a second. And then dynamic time warping. And then what they do is they try to find the right distance metric to be able to figure out when two things are actually related. Let me talk about the first one, because it's actually pretty clever. So what they do is they set up an RNN that has a single hidden layer, has an input layer and the output layer, and what they do is they feed the time series into this with some interesting provisos. They randomly pick the weights of the input layer and the backprop layer. And the only thing that they do is they adjust the weights that are in the hidden layer. So they pump it all through, and essentially it's like an autoencoder, right? They pump it through, they see what the other side looks like, and they figure out what the weights look like inside that hidden layer. That is the encoding that they use for that time series. Now they run all the time series through that same model, and what you get is a set of interesting vectors that are sort of states from this RNN that's there. And each one of these time series that has the same label defines a subspace or a subspace of all the vectors that have the same label. Then the problem then becomes, if I have a new time series or a set of time series, what I now do is I just determine which subspace it actually belongs to, right? And that turns out not to be a trivial problem, but it's a reasonably interesting problem that you can solve. And there's lots of simple techniques, but they have a very nice techniques that gives you the best understanding, because you have to actually go figure out the structure of that subspace well enough, so you can't just use a representative vector from it. You actually have to do more work than that to be able to figure it out. So they did this, some very nice results here as well. The data set they use is a slightly different one from UCI this time, and that includes some of the UCR data set. Again, the number of time series is small, and approximately 200 data points per time series, but this time it's multivariate. The typical multivariate time series in this case is about 6 different variables. Some of them are in the hundreds, but that's about the range of the data set. So what did we do? Yeah, well, again, we're kind of simple people, so we said, well, let's take our time series. First thing is, each one of these is a different length, so let's pad them with zeros if they're a different length, make them all the same length. Convert them all to images. Now, as I mentioned, sometimes you have missing data. In the case of an image, the missing data shows up as a row and a column that's essentially blank. It has not a number in it. So what we do is we use linear interpolation in the image to fill that in. So now all the images are filled in. Then what we do is we take each of the variables and we just stack them. Run them through the same CNN, so it looks like the same thing, except the image now consists of the image of all these stacked variables. Run it through, same notion of running it through the MLP, and in the particular instance that we're talking about, I'm interested in CPU, memory, and other things. There's about, actually it should be 4 variables that we actually pump through and see what the result looks like on the other side. So what I did was I ran this through for one of the subsets that there's some published data on. This is a data set from a robot actually failing, so different mechanisms of the robot are not acting correctly, and this is information that comes off of each of the sensors. So one of the papers published, this is the distance metric paper, a 5-fold cross-validation error on their training set and on the accuracy that they wind up getting for each of the 5 different data sets that they've got. And what's interesting is we get less error than they do, except in just one case, which is quite interesting, where, by the way, the data is the least. So we actually beat their result. Kind of interesting. Then remember the fancy one where they embed it into different subspaces, and then they actually find the match into the subspaces? Well, we beat them also, except in the 2 cases where there's not enough labels or enough data. So it's really fascinating that a very simple approach that we took by essentially taking everything that's off the shelf. We didn't do any invention of anything. We put everything together, and it works, right? So the moral of the story is, if you want to do machine learning, you don't have to invent everything from scratch. There's lots of beautiful tools out there. Be creative about how to actually get stuff together. So in our data set, we had 4 variables, right? Did I count correctly? 1, 2, 3, 4, yes. CPU, virtual memory, HDFS reads, and we have tons and tons of this data. Lots of missing data, extremely noisy, and oh, by the way, as I said, if data sets go on for a long period of time, we have like data set for a year, to think about how much data that is. It's really, really large, and this approach works extraordinarily well for all of those things. So we tried this thing very scalably on a week's worth of data, 2 weeks worth of data, a month's worth of data, 2 days worth of data, and the results are incredibly good. Let me share some of those. So on one of our customers, this is a cluster of, I believe, a little over 2,000 nodes. And this is, by the way, all the machines that I'm talking about are machines that are running customers solving production problems that are revenue problems. Right? Think about if one of these clusters is down for a minute, they may lose a couple of $1 million in revenue. Right? So we're talking about serious problems here. And you know what? We get pretty darn good accuracy across this thing, about 78% accuracy in being able to predict. And by the way we got the labels is the operators, when they actually submit the jobs, they actually label some of the jobs. And there are very few customers that actually label them meaningfully. Most customers label them as job 1 and job 2, or they put a timestamp on it. It's really, really informative. But there are customers who actually say, I'm solving a problem for click prediction, or I'm solving a problem for retrieval on something or whatever. So they have very well labeled data, and these are the customers that we're talking about here. So we're able to reproduce the stuff actually pretty nicely, with the exception of label 8, where we got 0% accuracy, and I need to figure out why. This is another data set, larger, much more variable in terms of the amount of labels that they've got. In this case, it's 48 labels. By the way, we have customers that have probably 700 labels on the data sets, which is completely nuts because they take the same thing and label it 5 different ways. So then you need to go to the opposite problem. But in this case, again, we're getting about 76% accuracy on the set of results that we've actually got going on here, right? So what's the moral of the story? The moral of the story is, if you can build it off the shelf and it seems reasonable, try it first before you go in reinventing new science, because you can actually solve very practical problems very nice way. And the funny part about this is we didn't try to go out and build sort of the best technique for being able to go do both univariate and multivariate time series analysis. We were able to do that from a classification perspective. So classification is interesting. The other thing that becomes much more interesting is we have the same data sets across many, many different servers, many different customers. What's interesting about that is that the characteristics of these jobs are actually are present in all the different clusters. So what we've done next is actually taken the data from every single cluster and mapped it into a uniform label set. And it turns out that across about 22 different customers on 25,000 nodes, we get about 60 different labels that tend to represent the vast majority, as in 98% of the workloads that get run on these things. That tells you something about big data workloads and how they behave. If we have that characterization now, since it's independent of the customer, we can take every single task, map it into one of our labels, and now we know exactly what the scheduler should do or shouldn't do with those things. That's kind of the next thing that we're doing in terms of implementing this stuff out. So it's actually going out into real systems. The last thing that becomes interesting is we talked about classification. Time series prediction becomes also interesting. So I've got a cluster that's busy. I want to put a new task on there. I've got a SQL query that a Hive query that I'm running. Should I run the Hive query now or not? Or should I wait another 5 minutes? Should I wait another 10 minutes? So we have this notion that we call the cluster weather. Is it stormy? Is it cloudy? Is it rainy? And is it clear? And how well can you actually do that? How well can you predict 5 minutes into the future, 10 minutes into the future, 20 minutes into the future, 30 minutes into the future? Turns out that up to 30 minutes, we can actually do a really good job. The technique there is actually, we had to build it. So we know the structure of the jobs. So a task belongs to a job, belongs to a node, belongs to a cluster. We actually build LSTMs for each of the cluster, or each of the hierarchy. All these are treed LSTMs. And it turns out that we're actually able to predict quite nicely up to 30 minutes out. So now, when somebody comes in and wants to submit a job, they can actually tell whether I should do it now or not, or I might be waiting for 2 hours before I get a result back. Right? So that's it. I got nothing else. Thank you.